Now we're going to take a look at some theorems involving groups. And so let's start with this theorem. Let G with some binary operation be a group. Then for all A, B, and C in G, we have that A, B equals A, C implies that B equals C. Also, B, C, excuse me, B, A, C, A implies B equals C. So these are called the left and right cancellation laws. And we can prove these. And we can say since A is in G and G is a group, there exists an inverse of A in the group G. Again, one of the properties of a group is that there's an inverse for every element that's in this group. Such that A inverse A is the identity, and that same inverse written this way leads to the identity. So then now, if we have A, B equals A, C, multiply both sides by A inverse on the left. So we're specifically multiplying on the left, because remember, it's a group, so we don't necessarily know that the members of the group commute. We just know that, again, if we multiply this, so now if we do this, so I multiply each side by the inverse, and of course, right over here, and like I said, there's a star in here. Sometimes I leave the star out, but the inverse, so then right over here, then this will be the identity, B, and over here as well, this will be the identity C, EC, and of course, the identity times B gives you B, the identity times C gives you C, like that. So we started out with this, multiply both sides by the inverse, gives us this. Also, The other one was B star A equals C star A, like this. Again, multiply this time on the right. By the inverse. This is the identity. This is the identity. And then we multiply the identity times B, get B. Identity times C, get C. So that proves the theorem that if you have members of a group and you have something like this, this implies B equals C. This also implies B equals C. Notice so far, we cannot say for sure, we cannot say that A star B equals C star A implies that B equals C. Because this time when we multiply, if we multiply on the left over here, or I'm saying multiply, but whatever this operation is, and on the left over here, like this, excuse me, AC, this is going to be on the left, this will be E, so we'll end up with B on the left, but on the right, we're not going to have, our identity because we just know that we have a group. We don't know if we have a group in which the members commute. So like now, if they could commute, then we could switch these around and then have the identity and have B equals C. So, but here we don't know that they commute. So we cannot say this. We cannot say that A star B equals C star A implies this. We can only say it if the members, like if A is on the left in both places here, or on the right both places here, we can make that deduction, but here we cannot. Another theorem says that for any group G, we have the identity element E in G is unique. B for each A in G, we said each A in G has an inverse. the inverse is unique. C, we can say for all A and B in G, we have the inverse of AB is equal to B inverse A inverse. Now I've left the operation, like the star off here, just to make it kind of simple, so the notation doesn't get too messy. I've left the star. This would really have a star here, and this would have a star here. Now let's see if we can prove these. So proof. So if we want to prove that something is unique, usually what we do is assume there's two of something and then show that they're the same. So like, let's say in this one here, so suppose there are two identity elements. And let's call them maybe E1 and E2. Let's assume there's two different ones in G. And so we're going to assume there's two different ones here. Then that means E1, E2, again, with some operation. I'm not going to write the star there, some operation between them. This is going to be equal to E2. Because if these are, let's say, if E1 is the identity, then when you take E1, E2, you're going to get E2 back. So then I can say that since E1 is identity, and then also we can say that E1, E2 is equal to E1. Why? Why can we say that? Because E2 is identity. But what have we shown here? We have shown that E1, E2 is equal to E2. E1, E2 is also equal to E1. So if they're both equal to the same thing, then the thing that they're equal to must be equal. So if this is equal to E2 and this same thing is equal to E1, then E1 is equal to E2. So we started with the assumption we had two identities and showed that they're really the same. Next thing we want to show is that for each A and G, the inverse is unique. So once again, just like the last part, if we want to show that there's a unique inverse, suppose for A and G, there are two inverses. say, let me call this A1 inverse and A2 inverse. We're assuming that we have two inverses. And then, similar to the last one, then what we're going to have is that A1 inverse is going to be equal to the identity, but also we're going to have that A2 inverse is equal to the identity. So from here, since they're both E, this implies that A1, excuse me, I should have just said A1 inverse is A2 inverse, like this. But then from the cancellation laws, that we had a little while ago, we can now say that since A1 inverse equals A2 inverse, once again, I'm leaving the stars out here. From the cancellation laws, we can say that this implies that A1 inverse is equal to A2 inverse. So they're really the same. So we assumed we had two different inverses for a given A, and we proved that they're really equal to each other. Now, we could have also, I think, done it this way. We may also have said something like this, that A let's say A1 inverse is equal to A1 inverse identity. Of course, you can always put in the identity, because identity times any element, the element itself. So starting with this, put in this, and then we can say that this is equal to A1 inverse A, A2 inverse, like this, because we can replace the identity with this, because A times its inverse is the identity. And then we can take away the parentheses. And of course, we have over here, this is going to be E. And then E times anything is the anything. So what we ended up having here then is A1 inverse is equal to A2 inverse. So again, shows that the inverse is unique. So we did it this way up here. We also could have done it that way. Finally, we want to show that for all A and B in the group, AB inverse is equal to B inverse. It's going to be equal to B inverse A inverse. Once again, I'm leaving the stars out of these just to simplify the notation. So again, we're going to prove that. So we want to prove so what this is saying, let me just write this out. This says that the inverse of AB is B minus 1, A minus 1. That's what this is saying, because here it has AB inverse is equal to this, so it's saying the inverse of AB is this. So let's check this by multiplying them out. So that would be the best way. So test it, test this. In other words, see if we get the identity. What we'll do, we'll multiply this times this and see if we get the identity element. So we're going to take this times AB. Of course, we can take the parentheses away. That'll be B inverse A inverse A, B. And of course, this is the identity element, E. This is B inverse E, B. And then, of course, the identity times B is B. Get this. Of course, B inverse B is the identity. So we started with this and got the identity. So we can check it the other way too. We can take AB times B inverse A inverse. That'll give us A, B, B inverse. Once again, this is going to be the identity. And then that'll be A, E inverse, A inverse equals the identity, like that. So we took this times AB and got the identity. So it really, that's really enough, because we said the identity will work on either side if it works on one side. But in any case, we did test it both ways. We took this times AB, gives you that. This times this gives you that. So it shows that this is the inverse of AB.